Hello, everybody. Hope you can hear us all.
Good morning. Good morning.
So, Hannah, I think you're going to do a quick introduction.
Yeah, absolutely. Good morning, everybody. I don't know if you can see me at the moment, but I am Hannah, and we have Steve from Aerospace Kinross today. Welcome, welcome. Oh, we can see me now in the corner. Hello. Welcome to you all. Give us a wee shout in the chat as well to tell us where you're from, what school you're at. We will be fielding some questions at the end of our session today, so please do sign on to the Menti link and be ready to ask us some amazing questions. So I'm Hannah. This is Steve. Steve is our cosmic pilot. He is our planetarium director, and he is now also president of the British Association of Planetaria. So he is very knowledgeable in all things space related, and is going to be giving you a fantastic talk today. I will be doing some practical activities with you today. We're going to be making some little rockets and some little Ingenuity helicopters. So hopefully you've had a chance to have a look at the materials we sent out to you, but I know that some people joined on quite last minute. So if you haven't got any bits and pieces ready, don't worry. We will show you how to make some of these activities and how to do it, and you can always try them again later on in the classroom. So without further ado, I will let Steve take it away for us this morning.
Welcome to our session again. So this is our broad frontier, and we're going to be talking today about rockets, space probes, and space telescopes. And as Hannah says, you'll have a go at building your own little rockets and other things as well. So we're going to begin with rockets because that's how we get to space. And I'm sure you've all heard the phrase, it's not rocket science. And so rocket science maybe seems like it's quite hard, but it's actually not too bad. We're going to come on to that in a second, but first, just a little bit about modern rocket history. So we first started sending rockets to space just after the end of the Second World War. And the technology originally developed for war was very quickly changed into sending rockets and satellites and things to space. And interestingly, the first thing we sent to space were fruit flies on board a converted V2 rocket from World War II. And we weren't very sure whether space was going to be safe for humans. And we decided to send animals first. I hope we wouldn't do that nowadays, but that's what happened back over 70 years ago. The Soviet Union sent the first dog to space called Laika, and they also sent the first human to space in the early 1960s, Yuri Gagarin. The Americans were behind in that early space race, but they very quickly began to catch up, and the Americans sent the first person to space. His name was Alan Shepard. So that's just a look at some of the early space race, and the technology moved fairly quickly from there. So yeah, back to that phrase. Have you ever heard the phrase, it's not rocket science? So maybe you're tying your shoelaces and it's a little bit difficult, and somebody might say to you, well, it's not rocket science. And you may think rocket science is difficult, but it's not. The basics of rocket science is fairly simple. Pointy end up, flamey end down. Now, there is some science in there as well, and it goes back several hundred years to this person here, Sir Isaac Newton. He was the first person to come up with the laws of gravity, universal gravitation, and the laws of motion. We can see our little rocket moving there in motion. And on the right, we have the Principia badge. That is the logo from British astronaut Tim Peake. So recently, we've had an astronaut in space aboard the International Space Station. There was a competition to design his mission patch, and this was the winning design because on it, we have the apple representing Sir Isaac Newton's laws of gravity and the rocket his laws of motion. And rockets are sometimes known as reaction engines, because when we look at Newton's third law of motion, that's how rockets work. To every action, there's an equal and opposite reaction. And rockets work in that way. There's an action, we push flame out the bottom of the rocket, and the action is it goes up, the reaction. So yes, that's the basics of how rockets work. Not that complicated, really. And these are some of our more modern rockets. These are SpaceX rockets. I'm sure you've probably heard of them. These rockets have changed from the ones from the past in the fact that they're reusable. So these rockets, the first stages, they lift off to space and then they come back down and land, and they can be reused. Previously, every time we sent a rocket to space, we had to build a new rocket. So imagine that you did that every time you went to the shops in a car. You had to throw away your car and buy a new one. You wouldn't go to the shops very often, would you? That's what we've been doing with rockets for all these years. And this is how we used to get to space. This is a Soyuz capsule. It's still in use today, but this technology goes back to the early days of space missions. Looks pretty cramped in there, doesn't it? Well, this is inside the new Dragon space capsule. It's a little bit more sci-fi. So this is the way, the modern way, that astronauts are getting to space, which is pretty cool. All right, so that's just a brief look at rockets. We don't have much time to go into too much more detail, but I'm going to hand you over to Hannah in a second, and you're going to have a go at building your very own straw rockets. Here at Aerospace Kinross, and when we're out with our Cosmos Planetarium, we do these practical workshops, and we use all these different types of rockets to show you how they work, from straw rockets to aquajet or water rockets, pop rockets where we use chemical reactions, and then we even have some really cool small amateur rockets where we use solid fuel. And just to show you some launching, some slow motion action here, this is the water rocket. They can launch quite high up. Pop rockets, not so high, but they are good fun because you never know when they're going to pop. And the solid rocket engine here, these can propel our rockets several hundred meters. In fact, so high, we have to inform the Civil Aviation Authority if we are launching those to make sure there's no aircraft flying over. All right, so the basic rocket design hasn't changed much since the early days of the space race. And there is some specific reasons for that. Rockets are pointy for the fact that they need to cut through the atmosphere. And the rockets have a fuel and an oxidizer. So in space, there's no oxygen to burn the fuel. So you need to take that with you as well. And the basics of rocket engines are you force that expanding gas through a nozzle at high velocity, high speed, and that will propel the rocket in the opposite direction and produce lift. So there we go. We can see you have a payload at the top, usually a guidance system, your fuel at the bottom. You then have your engine and your fins. And I'm going to hand over to Hannah now. She's going to explain a little bit more about things you need to think about when you're building your own straw rockets.
Okay, so we're going to have a go at making our own rockets in class today. So like I say, if you've managed to get the materials together to do this, you can join in with me live. But if you haven't got everything organised just yet, don't worry. You can always try this one a little bit later on and even make a bit of an investigation out of it. So we're going to create some little straw rockets. I have got in Blue Peter style, one I made earlier, just here, made just from paper and some sellotape. So you will need to do our rockets today, a piece of A4 paper. You will need a straw if you've got one. If not, we're going to roll up some paper and make our own paper straws today. You'll need some scissors and you'll need some sticky tape as well. And if you've got some pens or pencils, you can always decorate your rocket and make it look a little bit more snazzy later on as well. So we're going to think about these kind of things today. We're going to think about gravity, because the force of gravity is what we have to overcome to launch our rockets into the atmosphere or beyond the atmosphere. We need to think about the aerodynamics, so having that pointy end to help us cut through the atmosphere, or the air in our case, and those forces, those equal and opposite forces today. So we are going to be the thrust or the propulsion for our rocket. We're going to use our lungs, our breath, to launch our rockets when we are ready today. And we meant to remove that bit. We're not using chemical reactions today. It will just be our lungs. So we have to think about how high we can get our rockets to go, and how we maximise those forces. So a big deep breath to give as much thrust to your rocket as possible, and whether you want to add a cone or some fins to help stabilise your rocket. You can decide how many you want to add, how big you want to make them, and maybe do a little investigation to see which ones work the best. And think about the weight of your rocket as well. The heavier it is, the harder you're going to have to puff to provide that thrust. So we're going to stop sharing our slides just now so you can see me nice and clearly, and we're going to get on with making our rockets. So I'm going to use my camera to just show you what I'm doing here today. So we're going to start off with our A4 piece of paper. So again, have a try if you can do this along with me today. If not, you can do it later on. So we're going to start off by folding our piece of paper in half along the centre. Give it a nice fold there. And then what you want to do is cut your paper in half. My fingers are not working today. Here we go. We'll grab some scissors and just cut along that centre line. Oh yes, give a wee shout out to Condorat Primary School in Cumbernauld. Welcome guys, thanks for joining us. There we go. So we've got 2 half pieces of paper, 2 A5 pieces. So if you have a straw, you don't need to do this step. If you don't have a straw, you can try this today to make your own paper straw. So you need to grab something to roll your paper around. I've got a pencil here, and we're just going to roll our paper around our pencil. Try and keep it nice and tight so you've got a nice straw shape. A bit fiddly. There we go. So I'm going to roll it all the way around to create that lovely straw shape. There we go. And then just some sticky tape to secure your straw in place. I think I definitely should have been a Blue Peter today. There we go. So you want that straw to be nice and tightly rolled and sealed along its length, like so. So we've now got a lovely straw. Make sure you can get some air through there. That's important for our rocket launch. But as I say, if you've already got a straw, you can use that today. So you've got 2 different options if you haven't got some straws. So next, we're going to make the body of our rocket. So take that other piece of paper that you have left over, and we're going to fold it in half again into quarters. And then we're going to cut that in half. There we go. Like I say, don't worry. If you are struggling to keep up, you can always watch this back afterwards to catch up with us as well. So we've got our straw made from paper, or our drinking straw, whatever you've got today. Yeah, trying to slow down to make sure you guys have got time to do it along with me. So don't worry. There we go. So with our other piece of paper, we are going to make the body of our rocket. Now the most important thing to think about is that we need to have our rocket able to launch from our straw. So we want to roll it around our straw, but we don't want it to be too tight. We need to make it nice and loose so it's got space to launch. So we're going to roll it this way. So you've got a nice long rocket. So we're going to grab our straw, either the one you've got already or the one you've made today, and again just roll it along the length of your straw. And then you can loosen it off a little bit to make sure your straw can slide in and out of your paper roll. This is going to be the body of our rocket. So again, exactly like you did before, we're just going to tape up our rocket. There we are. And then we want to put a bit of tape over one end of our straw. We want to slow it, to seal it off at the top so that we can't get any air escaping from there. So just pop a little bit of tape across the top and then pop it on like so. And just fold those little edgy bits to make a seal at the top of your rocket. You can put another little bit around the edge if you want to. There we go. we've got the body of our rocket. Okay, but it doesn't look too much like a rocket just yet. So here is where you guys can do a little bit of design for yourselves. What would you like to add to your rocket body? So my example from earlier, I've made a little cone, and I'm going to show you how to do that. And I've added some fins. So you can decide, you can have 2 fins, 1 fin, 3, 6, as many as you like. But remember, the heavier the mass of your rocket, the more things you add to it, the harder it's going to be to launch into the air. But we're going to start with that nice cone because we need a pointy end, don't we? So with that last little bit of paper you should have left, I'm going to cut that in half again. Doesn't have to be perfect. We just need a couple of bits to add to our design. And then I'm going to cut a circle shape out of one of these bits of paper. So you could just do a freehand circle, or if you fold it in half and in half again and cut out a circle, a quarter of a circle, you'll have a nice even circle shape. So I'm going to do that today. I'm going to cheat a little bit. There we go. Nice arc there. And if I unfold that, we've got a pretty good circle. It's not perfect, but it'll do. And then if you just snip one of the sides right up to that center point, and we can overlap the sides and tighten it up to make a cone. So you could have quite a big, wide cone, or you can tighten it up slightly to make a nice pointy cone. You can decide. You are the rocket scientist, the design engineer today. You can decide how pointy you want your cone to be, or even if you want a cone at all. I'm going to pop a little bit of tape to secure it. There we are, we've got a tiny little hat. What do you think? Okay, so we're going to add that to our rockets when we're ready. So the sealed end, that's the top of our rocket. And I recommend just getting a little bit of tape or even some glue, and I'm going to make a little loop with my sellotape. I'm going to pop that on to the top of my rocket, and then I'm going to stick my cone on, nice and easy and quite secure as well. Hopefully you guys are keeping up with me, but don't worry, as I say, you can always finish these off after our session today. So the last step, if you want to, you can add some of these fins. So I'm going to put 2 fins on my rocket this time, but I'm going to make them quite big. So I've got one last little bit of paper left. I'm just going to cut it diagonally in half, like so. So we've got 2 lovely right-angled triangles, the perfect shape for our fins. You can make yours any shape you like. And then I'm going to fold, a little flap along the longer edge of my fin. Here we are, so that I can sellotape along here and stick it to my rocket. So I'll let you guys make some fins while I stick these on. There we go. So just a bit of tape along that fold, and then attach it to your rocket body. A huge fin, that one. Going a bit bigger this time. I wonder if that'll help it fly or not be as good. We'll have to test it and find out. Do a little investigation. Okay, I'm going to do my second fin. There we are. Some more tape along there. Okay, second fin in position. So I'm going to do a little bit of decorating on my rocket to give you guys some time to catch up if you've been making these along with me at school. So I've got some pens here. I'm going to add some details. So I'm going to put some nice orange flames at the bottom to make it look like we have some fuel to propel our rocket. But of course today it's just going to be our breath. I wonder whose goes the highest. Who's got the biggest lungs? Here we go. We could have a little competition and see whose rocket reaches the highest point. Maybe mark out some height markers on your classroom wall and see how high these will go. I think I'm going to pop some little windows on my rocket ship so my astronauts can see as they leave our atmosphere. There we go. There we go. And maybe I'll even put a little astronaut inside one of these windows. You guys can do your decorating a little bit later and spend a bit more time on it. There we are. Some very more like aliens in my rocket, but there we go. Some little astronauts in there. And maybe I'll even put something funky on the fins. I'm going to put Aerospace Kinross on that fin. And on the other one, I'm going to put my name. There we are. So hopefully you've got something that looks a little bit like this. Yours might look different, and that's great. We want to test all sorts of different designs. Because when we design new rockets, they go through all sorts of different phases and reiterations to make the best possible design. Lots of testing to see what works the best. So hopefully you are maybe ready for a launch today. We're going to pop it onto our launch pad. So our straw is going to go inside the body of our rocket, and we are going to get ready to launch. So again, don't worry if you're not quite finished. Keep working on your rockets and you can launch them when you're ready. But we're going to do a little countdown now and see if my rocket is good or not. Here we go. So we're going to go for a countdown. 3, 2, 1. Oh, that was rubbish. Hang on. Oh, that's a bit better. I obviously don't have very much puff. Let's try my other design with 3 fins from earlier on. Let's see. After 3, 2, 1. Oh! Not the safest of rocket designs. It landed on my head. But have a wee try. Make sure you point it upwards and not anybody's face and give it a launch. Here we go. Fantastic job. I'm sure you have made some wonderful rockets and your teachers are hiding for cover as they are launched across your classroom today. But again, if you haven't been able to do one alongside us today, you could always try one after our session. Well done, you guys. Back to Steve. Thank you very much.
Wow, Hannah, that was fantastic. Some amazing rockets there, and great to see the launch and the countdown as well. So if we could share the slides again, that would be great. Fabulous. Yeah, so we were go for launch, and what an incredible launch we had there. All right, so now that we've built our rockets, we know how we get to space. The next thing is to think a little bit about some space probes. Yeah, the reason why we build space probes is because as far as we know, we are the only life in the universe. But that seems a little bit strange because there's lots of other planets out there in our own solar system and also orbiting other stars. We call them exoplanets, planets orbiting other stars. And we have wondered for a long time whether there might be aliens out there. So we have sent space probes throughout the whole of the solar system now. We completed our first grand tour in 2015 when we sent a space probe all the way to the dwarf planet Pluto. Pluto is pretty cool, but it's a long way away. It's over 3 billion miles. And it took our space probe over 9 years to get there. It was called New Horizons. Now, we don't have time to look at the space probes that we've sent to all the planets, but we are going to concentrate on just one planet, the planet Mars. And believe it or not, getting to Mars is the easy part.
How do you get to Mars? If you want to send a spacecraft all the way to Mars, first you'll need a fast rocket to escape the pull of Earth's gravity. The heavier your spacecraft, the more powerful your rocket needs to be to lift off. Next, make sure you launch at the right time. Mars and Earth orbit the Sun at different speeds and distances. Sometimes they're really far apart, and other times they come closer together. About every 2 years, the two planets are in perfect positions to get to Mars with the least amount of rocket fuel. That's important. The total trip is over 300 million miles. Finally, make sure your aim is right. You can't shoot for where Mars is at launch time. You have to aim for where it will be when you get there. It's a lot like how a quarterback passes a football. Also, you may need a few thrusts to correct your direction along the way so you don't miss Mars. If all goes well, you'll get to the red planet in about 7 or 8 months. Then, if you actually want to land on Mars, well, that's a whole other challenge.
Yes, so getting to Mars is the easy part. Just a little bit about the planet itself. So Mars is around about half the size of the Earth. And if you were to look at the landmass on Mars, it's around about the same as Earth if you were to subtract the oceans. It's the last of the rocky worlds. In our solar system, we have 4 rocky planets and 4 gas giants. And Mars is known as a red planet because the surface is actually rusty. The surface is covered in iron oxide, and the common name for that is rust. And Mars is actually visible in the night sky at the moment. So if you get a chance, you go out, have a little look for it. It's the bright red, rusty coloured object in the night sky. And interestingly, we think Mars had oceans on its surface in its ancient past. And here on Earth, where we find water, we find life. So places that we're looking for life elsewhere in the solar system is places where there has been water, like Mars, or places where there is water. We now know there's some moons orbiting the gas giants that have oceans underneath their surface. And just a little look back in time to the different space probes we've sent to the surface of Mars, either the American NASA missions, and back in the 1990s, quite a long time ago now, we were sending rovers, robotic explorers, to the surface of Mars, which were the size of large remote control cars. As we get into the early 2000s, so the turn of the century, we're sending bigger probes. Spirit and Opportunity were launched in 2004. And they were only supposed to last on the surface of Mars for a few weeks, maybe months. But Opportunity lasted for well over 10 years. And it's only very recently, when a dust storm covered its solar panels, did it stop sending back images. And in 2012, so 10 years ago, our technology moved up a gear again, and we sent the Curiosity rover. And we can see Curiosity is around about the size of a small family car. And it's not powered by the energy from the sun, from solar panels. It has a small isotopic reactor, a small nuclear reactor on board, which means it can still travel along the surface, even 10 years after it was sent up there. It has its own energy on board. So Curiosity has been searching Mars for signs of life. And recently, Curiosity was joined by a new robotic explorer called Perseverance, or Percy for short. Now, Percy might look a lot like Curiosity, but the technology on board has moved on massively. And not only do we have the rover on the surface, this new rover, Percy has on board a little helicopter called Ingenuity. Let's have a little look at this new rover and its little companion, Ingenuity. Incredible to think it was just over 100 years ago humans took their first powered flight. In 70 years we'd walk on the surface of the moon with Apollo. The direct connection between those two events is Neil Armstrong had a small piece of that first aircraft in his pocket, and he took it all the way to the moon. We are now 50 years after the moon missions, and we actually have an aircraft, a helicopter, on the surface of a world that's over 300 million miles from us here on Earth. This is Percy, and this is Percy's companion, Ingenuity. down on the surface, you can only see just what's in front. Ingenuity, we now have a whole new way to explore the surface of Mars. Wow, that's pretty cool, isn't it? All right, so it's time for the second practical element. I'm going to hand you back over to Hannah, and she's going to show you how to make your very own Ingenuity helicopter. If we could stop sharing screens, and Hannah, over to you.
Thank you, Stephen. So we are going to make our very own miniature paper version of that Ingenuity helicopter. So you might have seen on the slides there, we sent a little template out to you. And I know, again, some of you just signed up this morning. So if you haven't had a chance to print off that template yet, don't worry. You can always try this a little bit later today. But on each piece of paper, there are 5 little Ingenuity templates that look a little bit like this. So you need to have one of these per person or per pair, however you're doing it in your classroom today. So obviously Ingenuity itself is propelled with power. It's got some motors to make those rotor blades spin. It's got 2 sets of those lovely rotor blades. We're just going to do one small one today, and we're going to have to provide, again, that thrust. We're going to be throwing them up in the air, and then we are going to be seeing them spin as they fall. So we're using a bit of air resistance, a bit of physics to help us with our little helicopters today. So all you need for this little activity is, like I say, one of our templates. There are 5 on each sheet. And you will also need a paper clip. If you haven't got a paper clip, that's okay. You need some sellotape instead, and I'll show you the 2 different ways to do this so you've got an idea. And you will also need some scissors again, so hopefully they're still kicking about from our first activity today. So our little template here, we've got a few snips with our scissors to make. So this is the front of our template with some of those logos on it. We're going to cut in 3 places. So we've got a little snip to make here, a little snip here, and we're going to cut right down the middle to form our 2 blades, our rotor blades at the top here. So if you grab your scissors, we're going to do a tiny cut just into that black line, just there. And the same on the other side. It's a nice simple activity today. You can make one of these with our template, but then later on you could see if you can alter this design. You could use a bigger piece of paper, a smaller piece of paper. You can make your blades longer or shorter and do a little bit of an investigation again and see what flies the best today. So 2 little snips just either side there. And then we're going to cut right down the middle and stop when we get to the body of Ingenuity. I'm going to snip right down the centre till you get to that black line, so you have kind of bunny ears at the top here. So nice and simple. These are lots of fun to play with as well. So once you've done your snipping, we need to do a little bit of folding. So we'll fold down these black lines here, first of all, and we're going to fold it back to the other side. So just where you've made that little snip, we're going to fold it back on itself. So it tucks in like that. Can you see? We'll just fold it over and tuck it round the back of your little helicopter. And then the same on the other side, we're going to fold this side over the top and tuck that in at the back So we're just folding it over to make a kind of lollipop stick effect. There we are. So it should look a bit like this. Very tasty paper lollipop. Here we go. Well done, you guys. I'm sure if you're doing it along with us, you're doing a great job. Okay, so we've got 3 more folds to make. First of all, down the bottom here, you've got a little black line just below the Aerospace logo. So we want to fold this up to the back, like so. So you've got a little tab at the bottom, fold it over. And this is where you can either use your paper clip if you've got one, or you can use some sellotape. So if you're using a paper clip, we're just going to slide that paper clip up onto that little tab just to hold it in place, like so. My camera's very bright, apologies. There we are. And then if you don't have a paper clip, just to add, this is just to add some weight to our helicopter to allow it to fall. If you don't have a paper clip, you're just going to wrap the bottom with some sellotape. So you can kind of decide how much sellotape you think is equal roughly to the weight of a paper clip to give it some weight to help it on its flying journey today. And then the very last step is to fold our blades. So we want one of these to go forwards and the other one to come back the way. So we're just going to make a little fold along that middle line there. So one blade towards you guys and one back towards me. There we go. So from the side, it looks a bit like this. Now you might think this reminds you of something when it's flying. A lot of designs are inspired by nature, and these make me think of the little sycamore seeds that fall from a sycamore tree. And it's using a very similar principle. So what we're going to do when you are ready, again, we're going to launch our Ingenuity helicopters. And if you stand up for this one, or you can throw them as high as you can and watch what happens as they fall. Here we go. And you see them spinning. Hopefully yours is spinning beautifully at school. You can throw them as high as you can. Woo! See if you can catch them on the way down again. And imagine that that was the real Ingenuity helicopter taking some images of the surface of Mars. There we are. They spin very beautifully. And again, you can do, like I said earlier, some investigations with these. You could change the size of your blades, you could change the size of your body and see if it makes a difference to how it flies. Excellent. You can also change the direction of your blades. So watch carefully when it falls. Which way does it spin? Mine spun that way. But if we swap the blades over and we push this one this direction and this one the other direction, it will spin the opposite way. Can you see? Give it a try and see how your little Ingenuity helicopters work, and you could do some testing and change that design. Well done.
Wow, that was amazing, Hannah. Thanks so much. Your helicopter was fabulous, and I'm sure some of the pupils at the schools will be great as well. All right, if you could share the slides again, we have one last thing to talk about with you today, and that is space telescopes. So we have lots of telescopes here on Earth, but they are limited by the resolution they can see on the night sky due to the thick atmosphere that they're having to image through. But if you send a telescope to space, you don't have those same restrictions. So this is the Hubble Space Telescope. It's been in orbit for around about 30 years now, and it's coming towards the end of its life. But it has changed our understanding of the universe compared to what we knew before. What Hubble has discovered is galaxies, so places in the universe where stars clump together in every direction as far as it could see. But it was built over 40 years ago, and although astronauts were able to service it, it is in low Earth orbit. It is coming towards the end of its life. But we now have a replacement. I'm going to come on to that in a second. But first, we have to think about the scale of our space rocket. So next to a rocket, we have one of those cool American school buses, just to give you an idea of the size. And the reason the rocket was built to that size was because it fitted inside the American space shuttle, which was the biggest rocket that we had at the time. So that was the biggest telescope we could send to space. But in astronomy, size matters, and this is a replacement for Hubble. This is the James Webb Space Telescope, or Webb for short. Webb was launched on Christmas Day last year on board a European rocket, Ariane rocket, and it's effectively an origami telescope. It was folded up inside the fairings of the rocket, which meant we could get a bigger telescope to space. But it was very nerve-wracking for the scientists on the day of the launch, because although our rockets are better than they used to be, sometimes they can still blow up. But once it got to space, I had another journey to take. I had to travel over 1 million miles from Earth to a special point where it now observes the night sky. And over the time of the journey, it had to unfold. There was only over 300 points of failure as the space telescope unfurled from inside the body of the rocket for it being ready to take the first images. So we had a nerve-wracking few weeks as it moved from low Earth orbit to the special space further out. But thankfully, it all worked perfectly. And size really does matter in astronomy. The bigger the lens or the mirror, the fainter objects and the further back in time you will look. The fainter objects you will see and the further back in time you will look. And it ups the resolution of the images. So you will see finer details if you have a bigger mirror or lens. So to scale, we can see there's our human Sylvia. And there is the Hubble mirror, 2.4 meters. And there is the wonderful Webb mirror. You'll notice the Webb isn't one whole mirror. It's lots of segments of mirrors that are joined together. So it was able to fold out. Looks a little bit like a honeycomb, doesn't it? And as Hannah was saying about the helicopters and sycamore seeds, this is a little bit like what bees do. And that shape is means that we can build these telescopes that can fold up and fold back out again. And this is the Webb Space Telescope to scale. We can see it's the size of a tennis court and 3 stories tall. It's incredible to think that we have the technology to send space probes and space telescopes of that size out into the solar system. And yeah, so Webb, unlike Hubble, is 1 million miles from Earth, a special point in space we call a Lagrange point. It's a place where the gravity between the Earth, the Sun, and the Moon is equalized out. So it's a stable point where the Webb Space Telescope can loiter over time. And it will stay in that stable orbit with only just small bits of fuel needing to use to keep it in that orbit for at least 15 to 20 years. You see the diamond shape there? That's the sun shield. It blocks the energy from the sun and means our instruments on board are super cooled and very sensitive to the parts of the spectrum that they are looking at. This is a really cool quote from one of the scientists. The Webb telescope is so sensitive to heat that it could theoretically detect a bumblebee on the moon. And the moon is over 300,000 kilometers or 250,000 miles from Earth. So it's incredible to think that that telescope is so sensitive. Although why bees would want to go to the moon, I'm not sure. One small step for be kind, I suppose. All right, so I'm just going to show you a couple of the images. The one on this side here on the left, on my left, I hope it is your left as well. The one with the extra spikes on the star in the foreground is the new image from Webb. The one on the right is the image from from Hubble. It has 4 spikes on the star. So the stars in the foreground, the ones with spikes, are just stars within our own galaxy. But the smudges you see in the background are actually other galaxies. And the Hubble image took 14 days to gather the data. So to see those faint galaxies, we had to open the sensor on Hubble for 14 days. Well, the Hubble from Webb, they captured an image that saw more galaxies in 10 hours. So as the scientists learn how to use this new telescope, we're going to see further back in time than ever before.
I'm just going to jump in, Steve, and just do a quick shout out for King Case Primary School in Prestwick. Thanks for joining us, guys.
Perfect. Yeah. Hello. Yeah. So the other difference between Hubble and Webb is that Hubble looks in the light that we see, the white light. So the white light that we see can be split into the spectral colors, the colors of the rainbow. But either side of that, there are other wavelengths of light that our eyes can't see. And the Webb looks into the mid-infrared. Now, infrared is light that we can't see, but we can feel it as heat. So if you're close to a radiator, you will feel the heat radiating off. That's infrared radiation. And why does Webb look in that light rather than the visible light? Well, if you look at these 2 pictures here, we can see the Hubble image. There's lots of gas and dust in the picture. Well, if we look into the infrared, we can lift the veil of gas and dust and we can look behind it. So this is the same image, but the one from Webb, we can see inside that cloud of gas and dust to where the stars and planets are forming. So within that cloud of gas that we can't see with Hubble, when we look with Webb, we can see stars and planets. And planets are the places where we think we will find life. So what do you think Webb will find? The beginning of time, strange new worlds, maybe alien life. Are we alone? Now, through Menti, you can give us some answers to what you think Webb might find. But of course, maybe one day we will be able to visit some of these incredible places where there might be life. And if you do, make sure you take your suitcase. All right, so that's a little look at rockets, space probes, and space telescopes.
10, 9,
And you may
ignition
wonder why we're so bothered about these types of things here in Scotland. Well, most people think of the space race as something that happens in America, where they've launched all these rockets and went to the moon. But here in Scotland, we built one of the instruments on board the Webb Space Telescope, and we are about to start launching our own rockets to space. So our broad frontier, as the title goes, our excellent frontier here in Scotland is the fact that we now have our own space sector. And each year, more people in Scotland work in the space sector. It's grown by 1/5 over the last few years. And it's only continued to grow. So when you leave school, you might have the opportunity to work at a Scottish spaceport and build satellites that will send to space on these rockets.
Got some answers to your question about what the Webb telescope might find, Steve?
Slides to change.
Steve, we've got some answers to your questions about the Webb telescope.
Oh, fantastic.
So we've got...
Hold on a second, the slides have just glitched there. I'm just going back to the right slide if we can. Yes, sure, if you want to give us some answers there.
Yep, so they say that we might find aliens, we might find a new planet, or specifically a new planet for us to live on that's habitable. It'd be very exciting. Or asteroids before they hit Earth. Another good answer.
Fantastic.
We shout out to Holy Trinity in
Yes, so
Cork as well. Nice to see you guys have joined us.
fantastic. Yeah, so this is just a look at some of the rockets here in Scotland. This is Orb X. This is a really cool rocket. It's built locally in the north of Scotland, near where one of the spaceports is going to be. And not only that, it is going to use biofuel, bio-rocket fuel. So fuel made from plants, not fossil fuels. And that will reduce the CO2 emission, the carbon dioxide emissions of these rockets. That's the gas that causes climate change by over 90%. So the environmental impact is reduced if you build your rockets and launch the satellites that are also built in the area to space without having to travel around the country or around the world. And just along the road from me in Edinburgh, we have the company Skyrora, and they have a research and design facility in Edinburgh, and they have a rocket engine test and manufacturer site just outside Glasgow. And in fact, they flew this rocket for the first time very recently. It did launch, and it didn't quite get as high as they were hoping, but in engineering, you see what works, what doesn't, and you change your design and go from there. Isn't that amazing? You don't have to go all the way to America to work on rockets, and we're launching them from here in Scotland. And back to the Webb telescope. It's a mega project that has scientists and engineers working on from all over the world. But here are some of the scientists in the UK. Again, isn't it incredible when you see the scale of that space telescope? I've been lucky enough to meet some of the scientists, engineers who have worked on Webb as we were preparing for the launch. So I was able to meet them and ask them some of the questions that you might want to ask as well. So I've got some of the answers that they gave me. And these are scientists here. In the top picture on the left, we have Professor Gillian Wright, and she works at Edinburgh, and her team built the mid-infrared sensor, one of the main sensors on board Webb. And that's one of the sensors that might help us detect alien life. So I'm going to finish with that thought. Wouldn't it be amazing to think that we find alien life with an instrument built right here in Scotland? And it is time for your questions.
Yeah, please do pop some questions up on the Menti app, guys, if you've got anything you would like to ask Steve, our expert today. You've got the QR code and the numbers there. We've had some nice answers already, so feel free to add some questions and we'll do our very best to answer for you. We'll give it a few minutes and let you come up with some excellent stuff. Here we go, we've got some already. How can people find out more about space? We've got that question for you,
Wow,
Steve.
that's a fantastic question. So with regards to Webb Space Telescope, there's lots of amazing resources here in the UK, as I say, because lots of the scientists who have worked on it are here. So I've worked on a space project called Space at Home. So the website is www.spaceathome.org, and you can have a look on there for lots of information on Webb and other space telescopes. You can look on NASA, the European Space Agency websites as well. And UK Webb Telescope has a fantastic Twitter page as well that you can follow. So I'd recommend those to begin with, but there's lots of amazing stuff out there.
I think we can maybe put together a little pack with some of
a little list
things in it, and we can send it out to all the schools that have joined us today. We've got the school in Cumbernauld. Yes, you are in Cumbernauld. Can you come and visit? Well, I would recommend get in touch with Skyrora, because they do have, that's where they are based, isn't it, Cumbernauld, and see if they can reach out to you guys and maybe get involved with what they are up to. We've got a hello from Glen Manor Primary in Moodiesburn. Hello to you guys. Thanks for joining us today. And
Hello.
an excellent question, what is used to power the James Webb Telescope?
So it's the telescope itself has some fuel on board, so it has some solar panels as well. So it uses energy from the sun to help power it, but it also has some fuel on board, which helps it when it has to correct its attitude in space. So the energy from the sun to power it will last as long as there's sun, so we don't have an issue with that. The problem we've got is the fuel on board will only last for a certain amount of time. But the launch to space was so perfect that that fuel will last 15 to 20 years, we think, to keep it in that stable orbit to where it is to send back those incredible images.
Brilliant, thanks, Steve. A question here, have either of you met someone from NASA? I haven't, unfortunately. Steve?
Yes, I've been lucky enough to meet a few astronauts. Yeah, and I've also been to the Kennedy Space Center and walked underneath the wonderful Saturn V. That is the biggest rocket that humanity has ever flown. Although we do have a new rocket that's going to go to the back to the moon very soon, called SLS, as part of the new Artemis program. So we're heading back to the moon very soon, and that is a NASA mission. But there's also lots of European involvement as well. And of course, we have a British astronaut, Tim Peake, and he's a fantastic person to meet. And he does lots of school visits and stuff like that as well.
Okay, we've got 3 more quick questions, and then we're going to have to wrap up. Unfortunately, we've had lots of fun today, though. Why did they make the telescope a honeycomb shape, the mirrors on Webb? Good question.
Yeah, so that's just the shape is designed, so just with regards to the surface area and stuff, it means that it can fold in on itself and it's easy to fold out. And each one of those segments can independently move. So when we're wanting to focus the light from the universe, we need to be able to move those mirror segments so that all line up and send it to the little other mirror that's at the top. And that's where the information gets gathered to go to the sensors, the camera sensors, and back here on Earth. So it's specifically designed as that honeycomb shape, so it could fold out safely.
Brilliant. How much fuel does it take to power a rocket?
So it depends on how much mass you're wanting to send to orbit. So if you're sending small, what we call cube satellites, so small 10 centimeter by 10 centimeter cubes, which is what we build here in Scotland, you don't need a big rocket. So you see the rockets that are showed at the end, the ones here in Scotland are not that large because we're not sending that much mass, that much material to space. But there's a new rocket in America being built by SpaceX called Starship. And Starship is going to be on top of something called Super Heavy. And that combination will be able to send over 100 tons of mass to orbit. And 100 tons of materials to space is incredible. It's a game changer. So this is what we're classing as our first interplanetary rocket. We'll be able to take enough mass not only to orbit, but onwards to the moon and Mars.
Thank you. Last question. How much air do astronauts need to take up to space with them?
That's a great question. So everything, so obviously there's no atmosphere in space, so you need to take that with you. But we have special scrubbers and stuff on board. So when you breathe out, you're breathing out carbon dioxide. But we have special scrubbers on board that filters out that carbon dioxide so we can get more air. So a lot of the air is recycled, but we do have to take some with us as well. So you'll notice astronauts, the ones that were on the surface of the moon, for example, they had the oxygen tanks on the back of their spacesuits, and they had oxygen on board as well. So they only had enough to stay on the moon for about 3 days. But the space station, it's been crewed continuously for over 20 years. So technology on there means that we can now recycle air and water a lot more efficiently than we could in the past. So we can now stay in space long term. So technology moves all the time. So we don't need to take as much stuff from Earth if we can recycle and reuse the air and water. So the astronauts actually are drinking some of their own pee, although it is all filtered and it's pure back to water again. But yeah, the more you recycle, the less you have to take with it. So recycling in space is very, very important.
I was going to add
Always
about
have to get I always have to get something about P in there as well.
I was going to add it if you didn't, so I love that.
Yeah.
So we're going to finish off there, guys, but thank you so much for everybody who has joined us. If you took any photos of your class running these sessions with us, making some of these rockets or helicopters, please do pop them up on Twitter, tag us at YoungSTEMLeader or at Aerospace Kinross. And we would love to see what you've been up to in class today. But thank you so much for joining us. Our
Thanks.
main mission is to create a space and aeronautics themed science centre in the heart of Kinross. So maybe one day you'll get to come and visit us in our centre. But in the meantime, we can come out to you to do lots of bits and pieces as well. So do get in touch. All right. Thank you so much, guys. And yeah, we'll see you later.
Bye, everyone.
Bye.